A few weeks ago, I was lucky enough to interview the one and only Rafe Levine. You may know him from his work in the Rust community, including the Zlem, Velo, and Piet GPU projects. You may also be familiar with a font that he's created, Inconsolata. Rafe is a world expert in high-performance 2D graphics, and his research in 2D graphics has caused him to have an interest in what's known as SIMD. SIMD is the ability for your CPU to execute one instruction against multiple pieces of data, and in many cases it's critical for performant numerical code. Unfortunately, there are some pain points when using SIMD in Rust, so Rafe has been sketching out some ideas for how to improve the situation. To cover that, he's writing a blog post, which I'll link in the show notes, and he's also come on this podcast to talk with me about it. We ended up having a really fascinating conversation about SIMD more generally. What it is, where did it come from, how it's useful, and how can we make the experience of writing SIMD in Rust a little better. The interview was totally unscripted, without any discussion beforehand of what questions would be asked. So I've gotten Rafe's permission to lightly edit our conversation to remove filler words and false starts and so on. Anyway, without further ado, here's the interview.
Hi, thanks for inviting me on. My name is Rafe Levine. I'm an engineer on Google Fonts, although I have to say that I am in this podcast only speaking for myself, that my opinions are my own and not those of my employer. And mostly what I work on these days is font rendering and 2D graphics rendering. Really focusing, it's a little bit funny that most of what I work on is GPU, but there's a component of that where you have to make the CPU side of it as fast as possible. And that's why I have this kind of rekindled interest in SIMD in the last few months.
Yeah, that makes sense. And people often talk about GPUs as like SIMD machines.
I mean, I think the way that I would probably characterize that is that there's a continuum of how much parallelism your computer is exploiting. And a GPU is kind of on the extreme side. If you don't have 10,000 threads, then a GPU is just, you're not using the capabilities of that machine. Whereas a classical scalar computer, you've got one thread. It's really doing one operation at a time sequentially on like one number or one unit of data. And SIMD is in the middle of that, right? So you've got one thread of execution running on the CPU, but it might be doing anywhere from 4 to 32, or even in some cases 64 operations in parallel, in lockstep at the same time.
These are done through what we call SIMD instructions, right? SIMD stands for single instruction, multiple data.
Single instruction, multiple data, right? And this is a distinction, like, that when you're on a GPU, you have this thing called single instruction, multiple threads, which is very subtly different than single instruction, multiple data. The hardware is actually pretty similar, but the programming model is completely different, because on a GPU, you have different threads. And so like the core of the difference, maybe we're getting ahead of ourselves, but like I find this stuff fascinating. The core of the difference is that if, let's say you have an if statement where you say if condition, then A else B, and on SIMT, you can write that as an if statement, and the compiler and the hardware will map that to what's called predication. So you'll have a predication mask. So you've got this vector of whatever you're working on. So the mask is going to be a vector of Booleans, might be like, let's say 32 wide is a really common, width for this, especially for GPUs. So you have a vector of 32 bools that says, is that condition true or false? And then you do A, but it's mask where it actually only does it for the lanes in the mask that were true. And then you do B, and it only does those for the lanes in the mask that are false. And then if you're all true or all false, then you actually skip that instruction because you don't need to execute it. And when you do have like some false, some true, that's called divergence, and that's less efficient. So when you're programming a GPU, you need to be very conscious about, like, don't have too much divergence, because that's one of the things that'll slow down your performance. So the hardware is actually similar. Like SIMD is the same hardware. You can write, if you're writing SIMD code, the difference is that you would be writing that explicitly, that you'd have one thread as opposed to 32 threads.
Yeah, and this is probably related to why, in sort of GPU development folklore, there's this feeling that branches are slow, or, at least as slow as doing both of them separately. Right? Although, since like you said, if there's no divergence, it doesn't actually have to, perform the other half of the branch.
Yeah. So it's that folklore is partially true. And I think it used to be more true than it is. I think modern GPUs actually resemble CPUs more. And so like a lot of the stuff that you're used to doing, like branches and indirection and stuff like that, actually work on GPUs today, but might not have worked really well, say 15, 20 years ago.
It's interesting. I mean, GPUs, they still are crazy. Like, you don't have a proper function calls on a GPU, right?
You do in CUDA,
Oh,
but you
yeah.
don't FX API.
You don't have it in like a Vulkan.
That's right. In SIMD, so
Mhm.
this is where things get interesting, because in SIMD, of course, you have function calls, but that function call is going to take all of the SIMD lanes with it. You're definitely not able to do like a function call on this subset of lanes and do something else in the other subset of lanes.
Yeah, so SIMD, it feels somewhat lower level than SIMT somehow. I mean,
Yeah,
especially once you start writing like actual assembly to make use of the intrinsics, then it starts feeling really low level.
that's right.
Okay, we've covered the basics of SIMD. So you write one
hmm
instruction and it does like 10 additions at the same time or whatever.
hmm Well, 10
Um,
is a pretty unusual
okay,
number. It's
16
almost
additions.
a power of two. You have maybe like a decimal SIMD machine that does 10.
Yeah, we'll wait until AVX 500 comes out and then we'll.
Okay.
These instructions, though, they're not like a total standard thing that can be expected to be in every CPU, right?
Right, right. So that's the next part of the story. And so, one of the things is when people talk about CPUs and CPU architectures, you're usually talking about a RISC versus CISC choice, where RISC means reduced instruction set computing and CISC means complex instruction set computing. And there's this kind of historical divide where older computers might have these very complex addressing modes where instead of saying, I'm going to add these two numbers together that are in registers, you might say, go use this register, fetch a value from this memory location pointed to by this register, increment that register, and then do the arithmetic operation on it. So that would be like a very typical CISC instruction, complex instruction. Whereas in RISC, you say, we're going to separate the functions of loading and storing and adding. So each function is actually doing like a really, really, really simple thing, like add these two numbers together, go fetch this from this location in memory, go store this in this location in memory or branch. And those operations that I just said, like that's basically the whole story, right? Like almost all of the computation, when you have a compiler and you're mapping it to what the computer is executing, it's really mapping it to just those instructions. That may be like 95% or more of the instructions executed. But SIMD like blows the entire concept of RISC away. The SIMD instruction sets are enormously complicated, right? I think in modern, like in something like AVX 512, which is the most sophisticated SIMD implementation, I think they're over 2,000 instructions. Like you have to scroll, right? Whereas you look at an ARM, which is a a beautiful RISC inspired instruction set, and there's like quick reference cards that fit on one piece of paper, right? It's just a completely different ball game. And unfortunately, like there's definitely a common set. So when you think about the obvious things of like do this operation, like add, subtract, multiply, compare, etc., on like an entire vector of operations, those are going to be pretty much the same across all all computers, all CPU architectures. But even something like, so there's an operation called minimum and maximum, right? It's very simple. And this also gets to what you were talking about earlier in branching, that, in a very classical computer, you don't have a minimum or maximum instruction. You say, if A is less than B, then choose A, else choose B. That's the usual way you would write that. In a RISC, you'd have that sequence of instructions that would compute exactly that. But in a CISC design, in a modern CISC design, which is SIMD, you have a min and a max instruction, and it just does all that logic. But the rules for floating point are slightly weird. Like, what if one of the operations is a nan or something like that, not a number representation? You've got these floating point numbers that are not really numbers. And so there's IEEE rules for what min does. And then there's the operation that the chip does, which is slightly different. And then that operation might be slightly different on Intel than on, or
Oh,
something
no.
like that. So it gets really complicated. But yeah, so you end up having these instructions that both do a lot of bulk data. They're operating on this vector of very typically 8, 16 operations at a time. And you also have typically more complex instructions that are being executed that are, like maybe a little bit of a semantic level up where you're saying minimum and maximum, or you're saying, select this mask select business. You typically have, like, that would be one way of doing if then else. You evaluate A, you evaluate B, and then you say select A or B based on value of that mask.
And so is minimum and maximum, is this an example of like a SIMD instruction that you can't be sure that like your user's hardware will actually have?
That's right. That's right. I mean, I think minimum and maximum. So, when you talk about this question of levels, and that's really also a very central question, because the capabilities, they keep on adding more and more and more, right? So you look at a very old chip and it's going to be missing some of these more advanced instructions. You look at a new chip, it's got everything. And so that's a real big question. How do you know what capabilities your computer has? And if you've got an instruction in the stream that your hardware is too old, that instruction was defined after that hardware came out, then you're actually going to get undefined behavior, right? This is a very subtle thing. People talk about assembly language typically doesn't have undefined behavior, right? Like an instruction, like for example, in C, if you add two signed numbers together and they overflow, that's undefined behavior. But you don't have that instruction on CPUs. You have an add instruction, and then the add instruction is almost always defined as having wrapping semantics. So the undefined behavior comes from, oh, the compiler gets to do these optimizations, assuming it didn't overflow, right? And then if the assumptions are wrong, then the compiler might do something really unexpected, like maybe, for example, have a comparison operation against a bounds, and then you write out of bounds data. This happens all the time. But executing a SIMD instruction that does not exist on your particular level of hardware is actual, real, undefined behavior at the hardware level.
How would it be defined except maybe to do something weird like crash, but like,
Yeah. Sometimes it'll crash. Sometimes it'll, like there's a whole menu of what the hardware will actually do when it hits that instruction.
is there some way to ask the CPU, like, what instruction set do you support?
Exactly. Right. So on Intel, it's called CPU ID. And on other chips, it's other things. Usually it's just sort of reading some kind of flags out of a word somewhere that says, this is the set of extensions. This is a set of SIMD instructions that I actually support. And so, obviously there's different approaches to this, that if you know which chip you're actually running on, then in Rust, you usually say target CPU equals. So you can say target CPU equals Haswell, or you can say target CPU equals native, which will go and read those CPU ID bits and compile the code for that chip. So you're good as long as you know what hardware you're running on. But a lot of times you want to write code that will run on any hardware. And so you need to have, like, this is called dispatch, and it's also called multi-version. So you need to write multiple versions of your code that use the different levels, because the new level may have new features that run a lot faster. And so you want to have multiple versions of that function. And then you want to do the runtime detection of what the chip can actually support, and then dispatch to whichever of those versions is actually supported by the hardware.
So the idea is that we only have a problem if we try and execute some instructions that's not supported. Like, just the instructions existing somewhere in the binary is fine. Okay.
That's right.
And then before we get to the point where we might do something that is undefined, might execute an instruction that's unsupported, one option is to read the set of supported instructions and then pick a implementation that only uses the instructions that are supported.
Right. Right.
When I do cargo install, it builds it from source. Like, it can build it, assuming it's going to run on my computer, right?
That's right. That's absolutely right. And so, that's a really interesting observation, because, there's some code that isn't going to change performance that much depending on what level it's compiled for. Because if you're talking about like the basic RISC operations, those are pretty much the same. Those haven't really changed since like the 90s. But when you're talking about SIMD, it can be the number of lanes. Like an old Intel chip is only going to have 128 bits wide SIMD, but a newer one, which is defined as basically like everything in the last 12 years, you're going to have 256 bits, and then really new Intel chips or actually it's more likely that there'll be AMD chips these days. The Zen 4 and Zen 5 have 512 bits. So you might have a performance difference of 4x if you've got something that's really numerically intensive between saying, just compile this for the most generic target versus compile this for what I know that my actual hardware can support.
And then, of course, if you do that, then you don't pay any cost in terms of choosing which to dispatch. You decide it at compilation time, and then
Right.
it's sort of fixed for that binary. You can't
Right.
copy it to your friend's computer necessarily and have it work. But
Yeah, if they don't have a Zen 4,
you
you get
should stop
that
being
delicious,
friends with them, maybe.
delicious undefined behavior. Yes, exactly. Best way to lose a friend is
So what does the situation look like in Rust?
Mhm.
Is it, can we do this?
So it's evolving in Rust. And so I'm particularly interested in it evolving in a more high level, more friendly direction. But the current state is that you have, for one thing, you've got all of the intrinsics, right? And I think we skipped over intrinsics versus assembly language instructions. And maybe we should
Oh yeah, let's
take
go
a
back.
detour. Right. Okay, great. So you've got this huge set of instructions. It can be thousands that you need to choose from. And traditionally, until I would say maybe 10 or 15 years ago, that the only really practical way to get these instructions is to write them in assembly language. So you're talking about low level. You're really dropping down to the very lowest level of the chip, where you're writing the exact instruction sequence that the chip is going to be executing. And part of that task is, the SIMD instructions are operating on registers, and you need to, which is a fixed number. There's usually like 16 or 32 SIMD registers. And so then you need to decide, instead of writing X and Y, you're writing, XMM0, YMM7, right? Which is really like, I actually personally kind of enjoy the puzzle aspect of writing that kind of code at that very low level. But when you start having to do like all of these different versions for, ARM and Intel being different, and then the different levels within each individual architecture, it really gets impractical fast. So the way that compilers do this is you've got intrinsics, and intrinsics have been evolving as well. And so an intrinsic is a function. So like you'll have an instruction and it might be called something like vadd_q underscore F32, right? Which would be the ARM instruction for adding a vector of 4 F32 floating point numbers, two vectors of F32 to each other. And of course, on ARM, it's vadd_q underscore F32. And on Intel, it's underscore MM underscore FAD. I don't remember. I might not have, I should have paired this in advance, but it's got this different naming. It's very inconsistent. It's very, very hard to wrap your head around. But at least you're writing X and Y. Like you can assign these vectors to variables, and you don't have to decide which registers they live in. The compiler will do its usual register allocation and kind of take care of that for you. In the early days, the compiler didn't understand anything about these instructions. It's like, I know I have to allocate the registers. When I say X, that's going to go into YMM3 this time, right? But other than that, it's like vadd_q F32. I have no idea what that is. I'm just going to take that intrinsic and know that I need to generate the fadd.f32 instruction in, ARM64 assembly language.
And it was like a complete black box as a compiler. Like it wouldn't do any.
Exactly. So the sequence, like when you're writing, the sequence would be the sequence, and the compiler would be doing kind of the very minimal translation of that into the actual assembly code that it's generated. And it wouldn't always do that very efficiently, because the number of registers that you have is fixed. And so what if you use more variables than you have registers? And that's, compiler will handle that. It'll generate code that works, but it'll do it by what's called register spilling, which means generally storing some of those variables on temporary stack locations instead of in registers. And your performance could just be terrible. So I think that in the early days of intrinsics, there was a lot of skepticism of, I'm reasoning about this in terms of, I know what instructions that I wanted to execute. Is the compiler actually going to do a good job of scheduling these, right? And like, for example, if you look at FFmpeg project, they have guidelines that are like, no, we don't do intrinsics. We're still in the assembly language camp. I think the rest of the world has pretty much moved on. Fast forwarding a little bit, that these days you have LLVM, which is used by Rust and is really pretty much the state-of-the-art code generator for compilers. It understands SIMD intrinsics really well. And I'll give you an example of the kind of optimization that AVX 512 has this instruction. There's actually blog posts on it. And the instruction is called VP turn log. And it's vector parallel ternary logic is what that stands for.
Whoa.
And so it basically will do any Boolean combination of 3 inputs. So for example, selecting from B and C, depending on the mask of value A, in Boolean logic, that's A and B, or not A and C. So in binary operations, you'd write that out as 3 instructions, and not, and or. And actually, even and not is a kind of a cool thing, because in Rust, if you're writing that out, it would be and, and then, so it'd actually be 4 operations that are combined. And the VP turn log instruction will do any of those Boolean combinations. So you can do XORs and ands and, any combination.
Does this mean you can have like any truth table you want?
Yeah, table. You put in the truth table.
That's crazy.
Yeah, absolutely. And so LLVM understands this very well. So if you're writing, you can write your logic just as ordinary Boolean logic. And then when it's compiling, depending on the target it's compiling to, it'll either do that sequencer of instructions, or it will say, hey, I can use VP turn log. This is really cool. I'm going to do this. So like these days, because LLVM actually understands those instructions and understands how to optimize them, that is the kind of only scalable way to write lots of SIMD code these days.
So okay, let's sort of go back up a little bit. We have these intrinsics. At some point, the compiler had no idea what was going on.
Right.
And wouldn't generate them, I assume. But now LLVM sort of knows what they do and is even able to use them to optimize your code.
That's right.
But this sort of happens like you write like and or not, like in a if statement, and then it generates using the proper instruction if it's supported based on your settings, right?
That's right. And there's actually another piece of this, which is called auto-vectorization. And auto-vectorization is exactly the same concept, where it knows what the intrinsics are and it knows how to optimize them, but your starting point is scalar code. So you can write Rust code that says for I equals 0 to 4, add the values in vector A, which is a vector of F32 semicolon 4, to B. LLVM will look at that code and it'll be like, hey, this is actually expressing something that can't be optimized into a SIMD instruction. And it will generate that fadd.f32 ARM instruction for it, or the corresponding add PS instruction on Intel.
Yeah, and I remember this being actually a sort of selling point for Rust at some point. There was this idea that, let's say you have a function that takes like a mutable slice and a immutable slice. Supposedly, Rust, using the fact that a mutable slice can't be aliased, would know that the other slice was pointing somewhere else. This would allow it to be a little bit smarter in how it implements auto-vectorization. I know that they have some flag for whether or not you should actually do this in LLVM that they keep turning on or off.
Yeah. No, I think yes. So that's landed. That's fully landed now. So you can have the LLVM aliasing analysis that will understand and respect the Rust semantics and say, hey, I can optimize this. I know that this is not going to alias. And therefore, I know that, for example, when I'm storing the results, those are not going to be overwriting the results that I'm loading. Therefore, I can now do it in parallel. That's the kind of thing that enables.
Okay, that's cool. And it's still by default, the Rust compiler by default is going to target this sort of very old, I don't remember exactly how old you said, but like 12-year-old or more instruction set that doesn't have any of the new fancy stuff that could be, multiple times faster in some cases.
That's right. And that, by the way, how painful that dispatch problem is going to vary a lot depending on what you're compiling to. Because if you're compiling to Apple Silicon, right, then that has all of the goodies. That has Neon, it has FP16, it has these 16-bit types in it. And so if you're compiling on Apple Silicon and you just say cargo build -- release, you're good. Whereas on Intel, it's this different story. The x86-64 target was defined kind of before the flowering of all of the good SIMD stuff. And so it's really stuck with SSE, which really comes from before the 64-bit days. And you're really not getting those benefits. So if you're on Intel, you're like, oh boy, I really better have, either specifying the target architecture or doing multi-versioning and dispatching.
I see. And okay, if let's say take a fancy SIMD instruction
Mhm.
that's for something recent, and I just stick it in my
Mhm.
Rust code, and I compile it, and then I send it to
Yeah.
my friend, it might not
Yeah.
work, right?
Right. And so this is one of the things that's evolving. Because that can happen in Rust today as we speak, and hopefully people in the future will be like, man, that was primitive way back then when they recorded that podcast, that all SIMD instructions are unsafe because there's no guarantee that the hardware will actually support that instruction. So it's basically this kind of up to you. Like, are you sure that you're actually going to be able to execute this instruction? And so you annotate that instruction, or you in Rust you annotate the intrinsic, and you say, I'm gonna call this function, which might be mm add ps, right? If you're on Intel, but it's unsafe. And so if you put that in your Rust code without the unsafe annotation, the compiler would be like, no, sorry, you can't do this. I'm gonna only let you compile code that you can give to your friend.
So
But
if you want to do
yeah,
things safely, it only lets you compile code that uses only old intrinsics, right?
basically none of the intrinsics at all. So it only lets you do auto vectorization. Like you write that for loop where you say, I'm going to add 4 floats in a vector together. It might or might not, right? Depending on, but no, in terms of like any SIMD instruction at all, no matter how likely it is that you're going to be able to run it, it's just unsafe and you just can't do it in Rust today.
I've never
Yeah.
used them like professionally, but when I'm doing something for fun, I was like,
Yeah.
that's weird. And I just write
Yeah.
unsafe and then I don't worry about it anymore.
Yeah. Absolutely. So as we say though, this is evolving because it is possible to do reasoning about when can I do this safely, right? And we can go into more detail, or I can just give you the basics that there's this thing called target feature. And target feature is an annotation that you put on the function that says, inside this function, I am assuming that I have at least these features, at least this level of SIMD capability. And then you basically have there's this new thing that's actually going to be landing, I believe, in Rust 1.86 called target features 1.1 that allows you a little bit better reasoning, where it's like if you're going from one function that has a target features guard on it into another function that has the same guard, that does not have to be marked as unsafe. It can do that transition safely because it says, I've already made the assumption, we've already kind of tested that this hardware is capable of doing it. So therefore, you have a pattern where you say, I'm going to detect, is this feature available? And then if so, then I'll call into my target feature annotated function. And that pattern is safe.
So then would I normally have would it be possible to have like 2 implementations of a function that have the same
Yeah,
signature? And then
absolutely.
somehow it just calls the right one?
It's not going to do that for you automatically.
Okay.
That's the fact. So you can express it, but you have to express it explicitly in Rust today.
I see.
And there's proposals, that, I mean, this is kind of like the cutting edge of Rust right now of can we somehow or another make this process more humane, so you're not sitting there manually writing like if x86 features detected, then unsafe call into this thing that has this target features annotation on it. I mean, nobody really wants to write a lot of that. And so I think, that's now the frontier because Rust, aside from SIMD, Rust is excellent at this. Rust is like, how can we reason about safety? How can we encode our safety invariants in the type system or encode, the safety into the design of the library? And there's a lot of stuff that you could do safely, but Rust today is just not smart enough to reason about that safety and say, okay, go ahead and just say, I want to add these vectors together and I'll multi-version for you and I'll pick the best intrinsics to actually make that happen.
Yeah, I feel like what everyone kind of dreams about is that someone else who's really smart wrote a library, and the library has a function that's called like add, and it takes two vectors.
Y- Yeah.
And, then they can just call it and somehow it'll do whatever's best.
True to some extent. So you have this library. There's actually a few libraries out there that try and kind of provide a safe wrapper around SIMD operations. And the one that's kind of the most mature, that people are really using is called, I don't know how to pronounce it. I'm just going to say FAIR. It's FAER. And it is like my own personal experience with it has not been fantastic because it's really organized around linear algebra. It's really good at linear algebra operations, matrix math, that kind of stuff. It does complex numbers really well, which I don't do a lot of personally. So I feel like it's not quite the right thing for me. But if you're doing linear algebra, you're doing fast Fourier transforms, you're doing that kind of stuff, then it's great. And it does exactly like there is a function that says, I have this vector of numbers. I just want to add them, or I want to do this,
Mhm.
butterfly multiply add or something like that. And then it has internally inside the library, there's all of this logic to say, if I'm generating code for ARM, I'm going to do this. If I'm generating it for Intel, I'm going to do that. I'm going to dynamically detect what my hardware capabilities are. I'm going to dynamically choose my vector width to be as wide as the hardware will support. And so that's the future. And the question is, how do you evolve the Rust language to make those smoother? And then the second part of the problem is, how do you extend this so it's not good just for linear algebra, but you can do these other, because you can SIMD, talk a little bit about like, what is SIMD good for? Because SIMD does not help you at all in that kind of classical object soup type of programming, right? But there are classes of problems where it is absolutely the perfect tool for the job. And the best case for SIMD is media codecs, doing compression and decompression of audio, video, and images, because you've got blocks of data, right? You're not just doing one thing at a time or making decisions on one thing at a time. You're always working on blocks of data. And at the same time, you've got like really complicated logic, like MPEG, the video decoder. It'll analyze the image and it'll divide it into these blocks of different sizes and then apply different compression algorithms on individual blocks. And that's something that, for example, GPUs are going to have a really hard time doing. But for SIMD, it is almost this perfect match because you're exploiting that parallelism on all the pixels or on all the audio samples, but you've still got that agility of being able to branch and make these decisions on a fairly fine grained basis. So that's like one class that SIMD is really well suited for. But you can also use SIMD on strings. And so, and there's like, if you look at Daniel Lemire, he's got a research group that is like doing all these like string Unicode conversions and JSON parsing in SIMD and so on and so forth. And you just say, I've got a chunk of 16 bytes of this string. And, I'm going to find out where the spaces are, right? That's just like compare with the ASCII code for space. It works really well for that. But as I say, this FAIR library is going to be a really poor choice for those kinds of applications because it just doesn't build out those kind of logic.
Did that So when you said SIMD on strings, I started thinking about like even more complex instruction sets, like if there was a SIMD to uppercase instruction.
If you're writing to uppercase, like if you're writing ASCII to uppercase, if you're writing Unicode to uppercase, you're kind of in a different world. I can actually walk you through like what does SIMD for to uppercase look like in ASCII, and it's really very straightforward because you're basically doing a comparison between lowercase a, which happens to be OX61, and lowercase z, which happens to be OX69. Don't ask me why I have all these memorized, right? So that's like two comparison operations. And then you do the and. So both of those comparison operations are going to generate a mask. So you're going to get ones or trues for all of the things that are greater than or equal to OX61, and another mask for all the things that are less than or equal to OX79. And then you and those masks together, and that's all the lowercase ASCII characters in your string. In order to convert lowercase to uppercase, you subtract OX20. So that we're going to get into predication and masks in just pretty soon, that you either have a predicated or masked instruction that says subtract OX20, but only do it for the lanes in which the mask is true. And then that's it. That's two upper. The problem is that how do you know, like if you know that your string is exactly 16 characters wide, you're good. But what if you don't know how wide that string is and you need to do two upper on an arbitrarily sized string? So now you've got a really painful situation because if it's a multiple of 16, it's no problem. You just loop over chunks of 16, but usually you're going to have a little bit left over at the end. And this is one of the most painful things about doing SIMD programming because you have to deal with this explicitly. And in Rust, you cannot load past the end of a slice. That is undefined behavior in Rust. That is unsafe. So you have an instruction that says load me 16 bytes at a time. And on older SIMD architectures, you don't have an instruction that says only load up to like 7 or something like that. But on newer designs, you have predication built into the hardware. So you can have a load instruction that says only do that load on the lanes that are true. So then you construct a mask that has the leftover, like up to 7 or whatever. And then you say, do that load that's predicated or masked. And so it only loads those. So Neon does not have that. AVX2, the older Intel style, does not have that. It's only AVX 512. It's only this very newest generation of SIMD that gives you a rich library of predicated instructions for doing this kind of string manipulation.
You can't even load it in Rust?
That's right.
Whoa.
Just loading it is considered unsound. And of course, storing is obviously unsound. Like that would be, and you have to store it too. But even loading, like that's the rules. Like if you have a slice of data, then any load operation inside that slice is fine, and any load operation that goes beyond the end of that slice is unsound.
Huh. That's interesting. So yes, this is a issue where like if your string is like 33 bytes long, right?
Yeah.
You have
exactly.
like 16, boom, 16, boom.
Yep.
Oh, what do I do now?
Yep.
And so in this case, if you're on AVX 512, you say, I mean, it would be kind of goofy to use the SMD instructions, but
No, you write the code that way. So you
Mhm.
basically say the way you would write this code in AVX 512 is that you'd say, how many chunks do I need? And you just divide by 16, but round up, right?
Mhm.
If you have 33 bytes in your string, then you divide by 16, and that gives you, 2 and 1/16. You round up, that gives you 3. So now your loop basically says, there's actually an instruction in AVX 512 for exactly this reason that says, give me a mask up to this size. And so if that size is greater than 16, it's just all ones. You're good, right? Go. And if it's less than 16, then it gives you the ones in the mask position that are inside the bounds and a 0 outside. So your code actually is really simple. It's divide by 16 and round up. And then for each chunk, generate the mask based on the size, and then load, and then do your string operation, which could be, we could then go through and do exactly the two upper that I just said. So that's a really nice piece of AVX 512 code. If you want to exploit SIMD and you're writing that code on something that isn't AVX 512, then usually what you'll do is you'll say, divide by 16, but round down, then do that loop on the chunks of 16. And then for the end, don't do SIMD, just do a scalar loop, like iterate 1 byte at a time for the stuff that's left over. And that's much more painful code because you have at least 2 copies. You've got the SIMD copy and then the scalar copy, which is going to be doing the same logic, hopefully, right?
Yeah.
I mean, because you're writing this explicitly, there's no guarantee that it's actually going to do the same thing. And it's going to get invoked when it's not an integer multiple of the SIMD widths.
And it may not be a problem in practice, but then you also have like a branch or I
Yeah,
guess
it is a problem in practice. Like, that's definitely, like, it's bloating your code size, it's bloating your branch, it's making branch prediction
Yeah.
less reliable. Whereas you go back to the AVX 512 code and like from there isn't a branch in there, it's generating mask bits, and that just, that just blows.
What's the dream for us to have in Rust? Like, where could we be going?
What's the dream? What does this look like? Yeah. So there's basically like 2 levels of the dream. And level number 1 is making the Rust language be able to express the safety invariants for, the levels and the different operations that are going on. And that's actually very complicated. We didn't talk about ABI. That's one of the things that makes it complicated. The ABI is actually different depending on your SIMD width. And so now you've got to mix different ABIs inside the same binary. And that has been, as you can imagine, a huge source of, bugs and complexity and so on and so forth. But, I think that they're working through that. So, so we need to make the Rust compiler so you can express, hey, this is actually safe. I've actually checked the CPU ID. So therefore I know I can call into this level of SIMD. And I think that's happening. There's some proposals on the table and I'm following that very carefully. And then you need the libraries above that. You need the abstractions where you're not thinking in terms of these individual very low level instructions, but you're thinking in a higher level. And again, for linear algebra, that's pretty straightforward because it's all combinations of adds and multiplies and so on and so forth. For the string type stuff or more complex data structures, you can do it, but we need to be a lot more creative. We need to be thinking about what are the primitives that are actually useful, and then they map portably and safely to whichever thing you compile on. But I think it's possible. I think, there's exploration. I've certainly been exploring it as well myself, and there are reasons to believe that we can actually get there. It's just going to take a lot of work.
That sounds super exciting. And then is it possible, down the line that, let's say for some reason you already know that you're going to have the dispatch overhead, at least at the beginning of your program or something, that LLVM auto vectorization could also be doing this? Or is auto vectorization going to be stuck always being super old?
No. We skipped over that. Absolutely. When you have that target feature block, right, then that enables all of the optimizations. That enables the use of those intrinsic. Then it also enables the LLVM optimizations to target those levels. So even if you're not writing explicit SIMD code, doing the multi-versioning and the dispatch is something that might be really useful.
I see. I wanted to ask about some existing Rust libraries before we run two at a time. There's one called Pulp
Sure.
and one called Fearless SIMD.
Yep, absolutely. So I misspoke a little bit when I was talking about FAIR. That is the linear algebra library that's on top of Pulp. So there's this layering where FAIR sits on top of Pulp, and then you could write code directly in Pulp and do your own logic. And so if you're doing linear algebra, great choice. A lot of really interesting designs. There's a lot of interesting representing the SIMD level as a Rust zero size type, which is if you're not familiar with your Rust, you look at that and you're like, what the heck is going on here? But it's just a way of representing, I have a witness to the fact that, I have the CPU level and I'm going to encode that in the type system. The trick is that you make your function polymorphic on the SIMD level, which is a zero size type. And so you write your code once and you get the generation of the different versions, the multi-versions for dispatch.
Because it has to monomorphize it anyway.
And so the monomorphization is expanding that out and giving you the multi-versions. And then Pulp has this macro. Every one of these libraries has this macro that does the dispatch and says, query the CPU ID, and then instantiate the zero size type that corresponds to that query, and then call into this monomorphized version of the function that you wrote. So that's kind of the trick.
Yeah, so
it works.
I guess in case anyone watching needs a bit more explanation, what I'm thinking is going on is you want a function to only be called after you've already checked something else. The thing that does the checking can sometimes return a type that's sort of the same as an empty tuple, but it just only returns it in this context in which the function is able to be called. Then the function takes it, and the only way for someone to actually call the function is to previously call the check function and looked at the output. And then since it's the type is isomorphic to the empty tuple, it all gets optimized out anyway. And it's you still do the check, but you don't actually pass anything.
That's exactly right. And so you're basically encoding the safety invariant in the type system, which is Rust's specialty. Mm-hmm. And in this particular case, you're encoding it using a zero size type. There, Like there are other things where, you'll encode it with like send and sync traits if you're trying to encode safety invariants about threads. And this is kind of the same story, but, this very specific, like, how do you do this? And then, there are proposals to make that a little less painful in terms of, like, do I always have to write these bracket, S colon SIMD bounds on my functions? And, maybe we can make that like easier. But
Yeah.
you can at least encode the information, and then the Rust compiler will then enforce safety, which is, that's the dream, right? You want to be able to write safe code. And
Yeah. I mean, even if it's not convenient, as long as you don't have to write unsafe, then at least you know generally that what you're doing is not
yeah,
totally crazy.
yeah.
I guess that's what
So,
Rust is all about.
so Fearless SIMD is a library that I wrote 7 years ago and did a blog post, and probably link to that in the show notes. And it never got used. It was basically an experiment. And I think I probably can claim credit that that's the first time that you were trying to encode the safety information in the Rust type system. Like, it innovated that concept, but it did not build out a rich, useful library of primitives. It just kind of showed like, maybe you could do this thing. And then if you go back and you look at that blog post, it was much more mixed than what we've been talking about, because it's like, okay, we can do this. And if the compiler was right, then it would do all this safe code. But then you start running into all these bugs with target feature, like mixing different ABIs together. And so it doesn't actually work. You can't actually, make this work. But in the 7 years since, Rust has gotten a tremendous amount better. And people have been building these other libraries like Pulp, that do that. If you go into the Fearless SIMD repo, there is a experiment of kind of like my like dream or vision for what I think one of these sophisticated libraries might look like, that does not just the linear algebra, but all the strings and other logic. And it's not fully built out, but it does kind of work. And there's one particular thing that I find very interesting, that you have these 16-bit floating point types that are very new. They're only supported on a small subset of the chips. But if you're doing pixels, 16-bit types are amazing, right? You get twice as much throughput. It's really good. And of course, in the machine learning world, it's all about doing more and more operations on smaller and smaller scalar values. There are FP4s. I think there's like research on like 1 bit, it's like, but for pixel values, for colors, FP16 is the ideal representation. And you have that on Apple Silicon, but you don't actually have those intrinsics yet in the Rust compiler. There's a tracking issue, and like there's all these details that have to be worked out. So Fearless SIMD does give you the PR2 on that repo does give you access. And the way that it does it, it kind of goes back to the bad old days of intrinsics where the compiler didn't understand what was going on. It actually does inline assembly. So it's
Nice.
not going to be able to do as many of those optimizations, but you can write code that uses 16-bit floating point arithmetic, and gives you access to that.
When I heard you wanted to talk about SIMD, I kind of wasn't that surprised. I didn't know that it was an interest of yours, but obviously you're interested in graphics. And,
Yeah.
Anytime someone's interested in graphics, it's like, I want to be doing this multiple things at the same time.
Yeah. And so, so that's another thing to talk about a little bit, that I've been doing all this work on GPU-driven vector graphics rendering. And for complex reasons, that I've been looking at, how many of those ideas can map back to the CPU. And I've been doing some experiments, and it's very promising that I actually believe at this point, and there's a big collaboration. There's going to be at least like 4 or 5 people working on this full time in the next few months, where we're going to be building out both a CPU renderer and a hybrid renderer, that you could describe it at a very high level as saying, we're going to do all the geometry and all the kind of complex logic on the CPU, and then we're going to upload that, and then the GPU is going to be painting the individual pixels. It's not going to be doing the geometry about where the boundaries of the shape and what clips against what other, shape. Those are very complex things to do on a GPU. So you do that on a CPU, and you SIMD accelerate the hell out of that, right? And then you upload like, okay, here are the pixels that need to get painted as a result of that geometry.
I've seen your old blog posts about like the stack monoid and stuff, which were
Yes,
about trying to do clipping and boundary box detection and things like that on the GPU.
exactly. So in the new design, yeah, I actually just did a research retreat last week. And so I was revisiting that question of how do you do that clip logic? And in the prototype, it's the clip logic itself is sequential, and it's just easy, right? There's a stack, and you just say every time you push, you just intersect that clip bounding box against the top of the stack, and every time you pop, you basically undo that. And so I was like, wow, if you're doing this in sequential logic, it's just so much easier than doing it on the GPU. And then I feel like kind of my dream, my vision is that one of the advantages of doing this hybrid method is that it's going to be way more memory efficient, that you're going to be able to do all these operations in bounded amounts of memory. Whereas if you're doing this on the GPU, this is a very serious problem of how do you predict how much memory it's going to need? And then if you run out, how do you deal with that failure? Because that's not something that GPUs handle well at all. So I kind of want to do this hybrid thing where you get the really nice memory usage and robustness and some other advantages, and also working well on down level GPUs because you don't always necessarily have advanced compute shader features. And then I want to get back to it. I want to say, okay, now that we've done this, how can we move this like complex logic and do it all GPU driven? And I think the SIMD is like, SIMD is a kind of an intermediate stage between doing things that are purely scalar and doing things that are so massively parallel that you have to like think about thousands of threads.
Yeah, that's actually really interesting to hear. As someone who's just following it, I was shaking my fist at Apple for not having the barriers that were needed to implement the prefix sum
Yes.
algorithm or something along these lines. Or there's
Yes.
like a fast version that was invented by NVIDIA that requires certain barriers. But then Apple redeemed themselves by adding all of the AVX 512 intrinsics.
The FP16, yeah.
Yeah.
Yeah. So that particular question about that barrier, we could do another podcast on that one. But we actually have a collaboration with Thomas Smith and John Owens. We actually have an academic paper that we're working on that actually
Oh,
has a solution that does not need that barrier. Figured out how to do it,
whoa.
only relying on relaxed atomics semantics. Good performance with no performance slowdown. So that was
Whoa.
a long story. That was a long journey to get there. But
We'll have to do a
yeah,
sequel.
there you go.
Um, well, that's awesome. Is there anything else that you thought would be cool to discuss? Or
There's so much more, but I think we've covered pretty good ground here.
I think so too. Well, thank you, so much for coming on.
Yeah,
I super appreciate it. Super enjoyed the chat. Um,
same.
awesome. Well,
Thanks
uh,
for inviting me. I'm glad I could be here.
great.